Welcome to the final session of the bootcamp. We've now covered all of the core material. That is basic terminal usage. That was session 1. Session 2 was a review of the basics of Python, all of the built-in data types, conditionals, loops, functions, error handling with try and except statements, and some of the built-in functions like any, all, min, max, dip, filter, and such. Then on Friday of last week, session 3, we discussed reading Python documentation and Anaconda and the kinds of things that are included in Anaconda packages, as well as multi-file Python programs. And Monday and Wednesday of this week's sessions, both 4 and 5, were focused on object-oriented programming. And so today, we only have about 10 slides or so. I don't anticipate the slides taking any more than 30 or 45 minutes. But what we're covering today is less things that are directly relevant right now, but things that will be relevant and will inevitably be relevant as you continue doing research and continue writing more and more Python code. So we will focus on some just basic concepts and basic principles of software engineering that can make your workflow a lot easier and can make things easier for you by organizing your code workspace. So I will go ahead and share screen. One second. Awesome. Can I get confirmation either verbally or in chat that we are seeing the title screen that says Basic Software Engineering? Thank you. Okay, so as promised, today is on basic software engineering. Obviously, we're not going to be going too in-depth. Software engineering is an entire discipline within computer programming. So these are just some principles that you should be aware of and bear in mind as you go forward in research. Some of this is likely to be, like I said, not relevant right now. But these are things that nonetheless you should be mindful of as you get better and better at programming just via practice. The concepts we're going to go over today will seriously help you down the line when you have potentially a very large code base that you've built for a research project. So to begin, just a simple definition of software engineering, and quite simply put, it is the application of the principles of engineering, like efficient use of resources, existing features and extensions thereto, and testing of the components and maintenance, and applying these principles to the code that you write. And the idea here is that if you're an astronomer, these things can be useful because a lot of times the code that we build for our research projects is complicated because the research we're doing is complicated. So if you are working with a code base which starts to get large, knowing how to engineer that code and knowing how to organize it are really saying the same thing. So software engineering is not about writing more code, it's about writing code differently. It's about writing code in a way that is more conducive to a relatively large code base. And oftentimes, when we say substantially large, what that refers to is anything that you may build, which you then come back to and feel the need to organize. If you have ever looked at your code and felt that the code that you yourself wrote is disorganized and is in need of just cleaning up, I know That is a pretty common feeling. People often in this field criticize their own code. Knowing how to engineer your code really is the solution to that, and it's really just rules that you can use to apply organization schemes to your code. And so substantially large in this case doesn't just mean production level software. It doesn't mean that you're building a Python package which you're going to release publicly. It might mean that you've just written a lot of code for a research project and you need it to stay organized. The first and foremost principle of software engineering in this regard, in terms of organizing your workflow, is the acronym DRY, which stands for Don't Repeat Yourself. The basic idea here is that you should never write the same code twice within an independent piece of software. In general, you should always assume that a piece of code that you write, be it a function, a file, or an entire application, however big it may be, you should always assume that every little piece of it is bugged in some tiny, subtle, nuanced way that is not necessarily apparent to you right now looking at it. The reason you shouldn't repeat yourself then is because when you do find an issue, obviously, we don't know what we don't know. The bugs that we have not found yet, we do not know what kinds of bugs we will find in our code in the future. The idea with don't repeat yourself is that you don't want to have to go and correct the same problem an arbitrary number of times. You want to make a fix to the code base once and have it propagate through the entire application, the entire software that you have built. The caveat to this is some Python packages, softwares are written in what people refer to as a modular manner. And what that means is that every component is implemented pretty much entirely independently of the other components. If you have a Python package, which is just a collection of calculations which are useful, and it is written in a modular way, what that means is that each calculation that it conducts is basically independent of the others. So some people will break the dry rule across modules. So they will not repeat themselves within the same module. The idea being that preserves the independence of the modules that are built into your software. So this rule does have some fluidity to it, but nonetheless, if you find yourself copy and pasting code, that in general is a bad idea. A lot of research scientists are notorious for copy and pasting code and making small modifications between the different copies. But in general, copy and pasting code should be avoided in the sense of this rule, and that is a direct violation of the don't repeat yourself rule. So moving on, another common rule that comes up alongside dry is a mnemonic named no ifs, ands, or buts, which basically just means everything you write should do exactly one thing. So if you have for every individualized component of your code, be it a file, a function, or a class, whatever, every individual component that you can isolate, you should be able to say what it does in a simple declarative manner that involves no ifs, ands, or buts. And there's the mnemonic. If you cannot describe what a class or a file or function does without an if statement, without an and or a but, then you should split it into more than one component. This file does blank, this function does blank, this class does blank. That you should be able to fill in that blank and make a simple declarative statement with nothing else to it. That very much helps in construction of large libraries, knowing that everything is going to perform exactly one purpose. And this greatly helps with organization as well. If everything you write does exactly one purpose, it becomes very easy to move things around in your code base. If you need to move code between files or move files between directories, knowing that they all do one thing is greatly useful in that regard. So this is something that aids greatly in what we call refactoring of code, which is not necessarily implementing new features. Refactoring just refers to sort of reorganization of the code base, just moving things around. If you find that you need it, version control is gratefully helpful in managing large code bases. When we sent out the survey at the beginning, one of the questions was whether or not you had used GitHub or Bitbucket or a similar platform. And that is really what GitHub and Bitbucket were built for, is version control. So if you don't know what version control is, it is really just a means of keeping a series of snapshots, for lack of a better term, of a given software's source code. And that source code may be anything from something as high of a production level as an entire open source distribution like the NumPy source code, which, if you didn't know, is hosted on GitHub. You can go and pull up the NumPy source code on GitHub and look at every single line if you want to. Bitbucket is basically the same idea. There are other packages that use GitHub for this purpose. And from the command line, this is this git command that I've been having you guys use. That's how you access these repositories of code on the internet. But GitHub and Bitbucket are useful tools not just for open source software, but you can also use it to as a very powerful tool to manage copies of code and plots, really anything, between multiple computers. I, for one, have this desktop that I'm running this bootcamp on. I've got my laptop right here. I have a desktop in the astronomy department, and managing the code base for my research projects and keeping copies of my plots is made very easy when I just simply store them in a Git repository and treat that as the master copy. Then when I change computers, I can just simply go to the directory where I have that repository downloaded. I run git pull, and then I am up to date. And it is exactly that simple. I don't have to worry about sending files between many computers to manage my workspace. It is essentially automated for me using GitHub. So if, not just a version control tool, but also a workspace management tool, GitHub is extremely useful in that regard. But from the standpoint of version control, if you decide to build anything substantially large, and again, that might not mean an open source software, that might just mean a research project with a large code base that you want to keep organized. Version control is very nice in that you can go and look back at previous versions of the code base if you find it necessary to do so. A couple of the next slides are more relevant for those who might be thinking of releasing something, but are nonetheless still relevant. And then we will end with a couple of the again, more general rules that could help pretty much any research scientist. So this, as stated, applies more to people releasing code publicly, but dependencies is something that you will always want to keep in mind if you decide to do so. Dependencies are any piece of your software that uses another external library. An example would be NumPy. Any of the Anaconda distributions constitute an external library or an external software, whatever word you want to attach to it. It is software that does not come pre-installed on a computer, which is required for your code to run properly. So if you write software that uses NumPy, then you would say, software engineers rather, would say that your code depends on NumPy. And NumPy nowadays is perhaps perhaps the most common, Python dependency. But the thing to keep in mind is that if you have too many dependencies, that is actually an extremely large problem. You should try to minimize dependencies. They are not a good thing. The reason being, I take an example, my own Python package is now 60,000 lines of code. If one of the dependencies releases a new version with changes that affect my code base, I have to go pore over the entire thing to make sure that it is compatible and doesn't break anything for my users. So that is why dependencies are bad. I don't want to go pore over all 60,000 lines of source code of the Python package that I've built. That is a task which is difficult and not easy to do. And so the advice that I give you, if you decide, if you think you might want to release software at some point, or you're looking at a series of routines that you've written and think that that other people may find them useful, and you are contemplating putting them out for public use, don't be afraid to write the small pieces which might be a little challenging yourself, and specifically in the interest of the minimization of dependencies. The reason being, then, if you write the small but challenging stuff yourself, it won't change unless you change it, and unless you as a developer decide to change it. Whereas if you have a dependency, then you're basically at the whim of the maintainers of your dependencies, and when they decide to release a version of their software that maybe breaks back compatibility with previous versions, and now you have to worry about cross-version compatibility between different versions of NumPy or SciPy or Matplotlib or whatever, then that can cause a lot of headaches and can actually be a big time drain if you find that you have too many dependencies. Perhaps the single most important piece of publicly released software is what is referred to as unit tests. This is the second of two pieces here, which are more relevant to those deciding that they might want to release something for open source use. Unit tests are simply a means of assigning a success or failure, or a skipped if the test is relevant for some reason message to the small components of a code base. The reason this is required, basically required in the eyes of software engineers, is that when you make future changes to the code base, your unit tests and the collection thereof gives you an automated means of finding out if the change you wrote just broke something. You can run the tests, just watch them go, and see if there are any failure messages that weren't popping up before. It's exactly that simple. And unit testing, even though it's it's something that a lot of research scientists haven't necessarily done, or at least haven't really thought that they've done, they more or less do on a daily basis. When you make a change to the code base for a research project, and then you maybe pull it into a Jupyter notebook or IPython, or maybe it's all in a Jupyter notebook, and you run it and just see that the output looks right, that really in of itself is a test right there. And when you make that test, if this is code that you are saving, a code that which is persistent and is in files, or especially if you're making it public, implementing your unit test is as simple as just saving that code. If you write code that ensures that the output of some function is realistic, we as research scientists sometimes tend to do that in a notebook or in IPython, or just looking at graphs. But just simply writing that code to figure out the success or failure message and then saving it along with the code base, that last component is all there is to it. Is you just simply take what you would write anyway and save it for future use. That's all. That's it. So there's two more of these. The last two are as stated, more relevant to those of you who might be working with a code base that gets relatively large throughout this summer and in subsequent research projects. But also not just for subsequent research projects, but if you decide to leave academia and go into any data science field, these principles will also be useful. So think before you write any code. This is one of the biggest differences between the coding practices that I've seen research scientists have and the coding practices that I've seen from software engineers. When a research scientist is posed with a problem, the most common response is that they just pull up a Jupyter notebook and start writing functions, or just start pulling in NumPy and SciPy, and they just start tackling the problem immediately starting with their code. That has its place and its usefulness within research. I will fully admit that if your goal is to play around with your data, then that is a perfectly fine thing to do, because you are by definition playing around. But if you're going to be spending even a small amount of time writing a code, or if it's code that you're going to be continuing to use in the future, if this is something that will even come up tomorrow, if this is more than just a one-off script, you should stop and ask yourself how you might actually want to write that code. What classes may be useful? How do you want to organize the data? What functions would be useful given that organizational structure? And this is a statement that came up when we started talking about Anaconda and all of the tools that are available to you. There are many ways that you can write the same program. So don't settle for the first thing that comes to your mind when you're building something that you're going to be working with in the future. The first thing that comes to mind is usually not the best idea you can come up with. And that's not a notion that is unique to software engineering. That's true for pretty much any form of art you can think of: visual art, writing, culinary art. The first thing that comes to your mind, you can usually improve upon. And this is exactly the same concept applies to software engineering. Just simply writing the first thing that comes to your mind may actually cause you headaches down the line. So I specifically want to call out that if you watch professional software engineers code, they don't start, and this is going back to what I said when this, something I said when this slide first came up, they don't start immediately in the text editor or the IDE or the Jupyter notebook. They start on a whiteboard or with a piece of paper, and they diagram a solution. They diagram and draw out by hand on paper the most efficient solution to the problem that they can come up with, and then they implement that. They don't just start writing functions. This is perhaps the most striking difference between scientist written code and production level code is not necessarily error handling. It's the flow of the algorithm. The final thing to end, I'm ending with perhaps the most important thing here. The bottom line, last but not least, the end all be all kind of rule number one of software engineering is that you will read your code a lot more than you write it. If you don't believe me, take one of your Jupyter notebooks and ask yourself how many times you went and looked back at a def statement that you wrote. You wrote it once, but I guarantee that you went and looked back at it more than once. So in general, you should assume that this applies to every single line of code that you will ever write in research or outside of academia. If you are ever writing code, every single line that you write, you should assume that you're going to read it more than you write it. And so with that in mind, you should always emphasize readability of your code above all else. The things that we have covered in the subsequent slides, like dry and no ifs, ands, or buts, there are gray areas to those rules. And if you find that And if you find that your code is more readable if you break dry or if you break no ifs, ands, or buts, then that is okay if that is in the interest of readability. So the idea here, this somewhat folds into what we were talking about with documentation last week as well. If you write code which is convoluted and don't document it and then come back to it months later and have to spend time figuring out what it does, what that means is that you did not write code which was readable in the first place. And you can save yourself headaches in the long run and make your workflow a lot easier and a lot more comfortable. And that also makes you a much happier programmer if you just simply write readable code and focus on making your workflow nice and organized from the word go. This long block here that I've written is sort of a summary of if I were to make a big public rant about bad coding practices in research science, this is the basis of that. In that if you view code simply as a means to an end and you don't care about anything else, that will only cause you problems. And there's no escaping that. There really is no escaping it. And I'm not just saying that. There is a reason that software engineering is a field. There is a reason that that is a thing. And it's that if you write code in a disorganized way, it will come back to haunt you inevitably. And again, the substantial size thing here is a line that is usually crossed long before you consider a public software release. If you are just simply working with a large code base and you feel like you need to organize things, that means you have crossed that line. And the solution to that is knowing how to engineer your code. So just a general piece of advice here is that if you are unfamiliar with a person's experience with software engineering, especially if they are not familiar with some of these concepts like unit testing and version control and minimization of dependencies, I advise taking the advice you get from research scientists with a grain of salt. We work with some very well-respected people in our field, and no disrespect to them, but however well known you are in your field, if you are not a software engineer, then however well known you are has absolutely no bearing on your own coding practices. So it's worth keeping in mind that software engineering is not the specialty of the people we surround ourselves with every day, and so the advice that you get may not be very well motivated. So if you are the type of researcher that thinks you might want to release a public software, these are the kinds of things you should be aware of, and these are the kinds of things that you should maybe talk to. Maybe break the astronomy barrier and talk to some folks in CS departments, or talk to some professional developers and get advice from them on how to effectively script a Python package or a public software release. So with that, that is the end of these slides, and I just want to say to those of you who participated, thank you for doing so, and I hope you found this bootcamp useful. So if there are questions about what we covered, we'll wait 10 seconds or so if anyone has some questions about these concepts.